Hello and welcome to this video. This is the first in a two-part series on polynomial functions. In this video, we describe the concept of Lagrange interpolation and how we can establish a bijective homomorphism, in other words, an isomorphism between polynomials over a field and polynomial functions over that same field. We begin with the definition here. For a field f, we define f of x superscript n to be the set of polynomials of degree at most n over the field f. For a field f, we define f of x of f to be the set of polynomial functions over f. This consists of functions g over the field f, where g of t is equal to f of t for all t in f and some fixed polynomial f over the field f. Now we define the map phi from the ring of polynomials over the field f to the set of polynomial functions over that same field f. And this map is defined by the relation f prime of t is equal to f of t. In other words, any given polynomial function mapped by phi over an argument t is defined to be equal to that same polynomial over the field f evaluated at t. So on the left we have a polynomial function that takes in an argument, and on the right we've got a polynomial expression, and that has formal evaluation. We now have this theorem by Lagrange. If T0, T1, T2 all the way up to Tn is a list of n plus 1 scalars from the infinite field f, we define the polynomials Pi as the Lagrange polynomials by the product over j not equal to I of x minus tj divided by ti minus tj, and this runs from indices of I between 0 and n. Given this definition of the polynomials Pi, any given polynomial f of degree at most n over the field f can be written as the sum, as j goes from 0 to n, of f of tj pj. F of tj is the evaluation of the polynomial over the field f at the point tj, and pj are the Lagrange polynomials we have just defined. In other words, f is written as a linear combination of the Lagrange polynomials with the scalar coefficients given by the evaluations of f at these points, these special unique points t, j. In order to prove Lagrange, one must first show that the polynomials Pi are independent. To that end, first note that Pi of tj is equal to delta ij. This is easily verified because Pi evaluated at Ti from the expression before just turns all these fractions into the number 1, into the scalar 1. The numerator and denominator are all equal to each other in this case, and so we just have that Pi equals the product of many different 1's, which is equal to 1. In case tj is different from ti, then we have that exactly one of these fractions cancels out to 0 in the product, and so the entire product cancels out to 0, because for one of these terms of the product we are going to have chosen tj minus tj. For others, we will just simply have tj minus tj prime. where j and j prime are both different from each other. Now suppose that the polynomial g is given as a linear combination of the pi's. G evaluated at the instant tj gives ci pi evaluated at tj, and by the relation established before, pi of tj equals delta ij, we have that this sum evaluates out to cj. So therefore, if g is equal to 0, it follows at once that cj equals 0 for all j, and the polynomials pi are independent in f of x. It also follows that pi, being of degree n, must span the space of f of x to the power n, meaning the polynomials pi form a basis for the polynomials of degree at most n over the field f. So now we complete the proof when we combine this result with the observation star. We now have the result that f itself is given as a linear combination of the pi's, with the particular coefficients being f of tj equal to cj. Next we have a lemma. The evaluation map as defined before, phi from f of x to the polynomial functions over f by f maps to f prime is a morphism of linear algebras. To show this, we first show that phi preserves the vector space structure of f of x. Indeed, cf plus dg prime evaluated at t is equal to cf plus dg evaluated at t as polynomial expressions. That then simplifies by the expansion of the bracket as cf of t plus dg of t for all t in f. And finally, it follows that cf plus dg prime is equal to cf prime, because this function is cf prime and this dg at t is nothing but dg prime. So similarly, it can also be shown that fg prime is equal to f prime g prime, and we show that right now. Indeed, for t and f, let us compute. Fg at t is given as the sum of fj xj over the indices j times the sum of gk xk over the indices k evaluated at t. This now gives fj gk times x to the power j plus k over the cross indices j cross k evaluated at t. We can split up now the evaluation of x to the power j plus k at t into t to the power j times t to the power k. We again separate out the two polynomials, polynomial products, and then we have the sum of fj tj over j times the sum over k of gk tk. The left term is nothing but f evaluated at t, and the right is the term of g evaluated at t. So that shows that fg evaluated at t is nothing but f evaluated at t times g evaluated at t. Finally, we have the main result of this video, the evaluation map phi from the linear algebra of polynomials over x to the linear algebra of polynomial functions over f defined by f maps to f prime is an isomorphism of linear algebras. It only remains now to show that phi as defined is bijective, since we have already shown it as a morphism of algebras. So to that end, surjectivity is automatic by the very definition of polynomial functions, because each polynomial function is nothing but a map under phi of a polynomial expression over f, For injectivity, we use interpolation by Lagrange. So let T naught up to Tn be a string of scalars from the field f, and let f be a polynomial expression over the field f of degree at most n. Now suppose that the polynomial function that f maps to under phi, in other words f prime, is equal to 0. That is, f evaluated at t vanishes for all t in f. It immediately shows, or it immediately follows, that f evaluated at tj also vanishes for all tj, and thus f as a linear combination of the pj's must have coefficients f of tj, and f of tj is nothing but 0 from Lagrange. So we conclude that f equals 0, where we use pj as defined in the formula for Lagrange interpolation. So it follows that f is injective because f prime equals 0 forces f, the argument of phi, to also be 0. And with that, we come to the end of this video. We have proven now that the morphism from the linear algebra of polynomials over f to the linear algebra of polynomial functions over f is in fact bijective, and so this is an isomorphism of linear algebras. Thank you very much for watching this video, and please stay tuned for the second part of this two-part series.